So let's continue. So if you remember, I mentioned before that we will consider 3.5, 4 classical base techniques for private estimation. So input and output perturbation are the most natural ones. And the next one we're going to be called sufficient statistics perturbation. So what is a sufficient statistic? Again, a moment about statistics. Sufficient statistic is a quantity, a function of the data set, which is sufficient in the sense that if you want to estimate something, knowing this statistic is all you need. For example, if I want to estimate the mean of some distribution from a data set, the empirical mean is a sufficient statistic. Knowing the whole vector of values that I sample does not improve in any way my ability to estimate the mean of the underlying distribution above just knowing this is my empirical mean. This is a sufficient statistic. Same goes for variance in several cases, etc. It's not always true. For example, if I want to estimate the confidence interval of my mean, then just knowing the empirical mean doesn't tell me the whole story. Maybe I want to know the variability of the points, etc. But sufficient statistic is a quantity that this is what tells me the entire story. In linear regression, we have very clear sufficient statistics. Remember, the linear regression, the ordinary least squares equation is x transpose x inverse times x transpose y. So the sufficient statistics are x transpose x and x transpose y. Again, they have an important intuitive interpretation. How the x values are distributed and what is the signal y sort of in the coordinate system of x, in a way. These are the two quantities. So, whenever there are sufficient statistics, I can always try to do the following thing. Let's estimate privately these sufficient statistics and release them. And then whatever is the calculation you do with these values, that's already post-processing. Again, if you can estimate the sufficient statistic in a private manner, always works. But now you need to estimate what will be the effect on the accuracy. Right? Because maybe slightly perturbing the sufficient statistics significantly degrades accuracy. Maybe the model is relatively stable. So the same way input perturbation always works, but it might completely ruin the accuracy. Sufficient statistics, had you managed to prove to bound the sensitivity of the statistics, always works, but again might completely ruin privacy. Okay, so let's think for a moment. What will be the sensitivity of each of these two quantities, x transpose x and x transpose y? Again, reminder, we assume each row of x is bounded by it has L2 norm bounded by 1, and the y value is bounded by 1, an absolute value or not, whatever. So what is the sensitivity of these two quantities to changing a single element? So maybe we should try with x transpose y. That is, in a way, a bit cleaner.
What we said about the A is bounded by...
What do you mean? The x, not the A. The A is already x transpose x. X, each row is bounded by is a vector with L2 norm bounded by, let's say, 1 for simplicity, or some constant c. So notice this quantity, B, x transpose y, can be rewritten as the sum of the rows, just transpose, so now they're vectors, multiplied by y. Now, what is the norm of each row? At most 1. Multiplying it by y, which is again about 1. So this is a linear query of vectors of dimension d with bounded range. So linear query, just add Gaussian noise. Right? So x transpose y is equal to sum of xi times yi, a vector of norm at most 1 multiplied by a number at most 1, altogether still a vector within the radius 1 ball. Therefore, this is a linear query, sum query. I can add Gaussian noise and I'm good. Similarly, x transpose x is a sum of outer products of vectors with themselves. So outer product is, instead of x transpose x multiplying the vector with itself to get its norm, it's an outer product, so it gives me a matrix. This is a large matrix of rank 1, and you do the math, the L2 norm of the entire matrix, of the entire d by d matrix that you get this way, is also bounded by 1. So even though this is a d by d matrix, it's L2 norm in the sense of, if I think of this matrix as one long vector, is still 1. So I can simply add Gaussian noise to both of them, and I'm done. Specifically to x transpose x, I will add Gaussian noise that will ensure that the matrix is still symmetric. And how do I do it? So one way to do it is to sample a Gaussian matrix and then add the matrix plus its transpose. Right? So any matrix plus its transpose is a symmetric matrix. But whatever, or you sample only half and flip, same thing. Okay? So I can add noise to this, I can add noise to that. I release both of them. Sensitivity is 1, I know how to do it privately. We're good. What will be the effect on the privacy and the accuracy? And so now we know privacy, and now we're not like in the output perturbation where I said I don't even know how to do it in a private manner because sensitivity is unbounded. Now sensitivity is bounded, but what is the effect on accuracy? So let's think of it. These are the points. This ellipse, is the sort of the way we visualize its covariance. But we don't use x transpose x in the final expression. We use its inverse. So what does it mean? The inverse of the matrix now becomes larger in the direction that was previously smaller and smaller in the direction that was previously larger. So the sensitivity is exactly flipped. So this quantity is the inverse x transpose x, and the direction in which the sensitivity is larger is this direction, exactly where we saw before that it's somewhat degenerated. And then there's also x transpose y, which is like a point, a center. Right? So I'm not sure how to draw it, but in a way there are two quantities. There's the ellipsoid, which direction does it look in how oblique it is. And then there's where the center is, that is the vector x transpose y. And when we change one element, we know what we do. We change this by somewhat, and this location by somewhat. We add the noise. When we add noise to this direction, we're not affected by much because there's a lot of signal. This is what this tells me, is that things will not be very significant here. When we add noise here, things will change more. And this, in a way, is where the same thing we saw before, that if there's a degenerated direction, we're very sensitive. That's why we won't really be able to run away from it. So what would happen now is we're always private, but we'll have degraded utility. So this is what it would look like. So now we're back to the same setting as we had before, where I change one element and see what it does, but Now I do it in 3 dimensions. So how does it work? This is the distribution of points, and this is the point I can change. Again, there's a y as a function of x function here, which is reflected by the color gradient. But I would start with changing the y of the point. Okay, so here I'm changing the y of the point. And nothing in the model changed. Why? Because the point is exactly in the middle and has 0 effect. Okay, now I will start moving the point. Oh, it turns out that it doesn't change because something broke in the present, in the... Ah, crap. It looks so cool. When did that happen? Oh man. Okay, so I have to tell you what it looked like. That was maybe the coolest visualization we had. So my point was that as your point is closer to the center, changing its y doesn't have a big effect, as we saw before. As it moves away, it affects both the covariance, it changes the covariance and the center. So basically this tells me the entire model. Where the center of the ellipsoid is corresponds to x transpose y, and the shape of the covariance corresponds to x transpose x. And as the point move away in the direction where there's larger sensitivity, changing its y has a bigger effect. So, what will be the result? So, first step is let's do exactly that. It's called analyze gauge. That's the name of this algorithm, which is exactly that. Let's add noise to x transpose x. Let's add noise to x transpose y and see what happens. So here's the visualization. Again, still working on it, but what we see here is the following thing. There is the dashed line, and the central bigger point is where is the point corresponding to x transpose y and the ellipsoid corresponding to x transpose x based on the data. And this is the step that the interactive plot was supposed to drill into our intuition, is basically changing the data will shift my ellipsoid, right, by moving its center, which corresponds to x transpose y, and change the ellipsoid itself, its direction and its size, by controlling x transpose x. Okay? So if I add noise to both x transpose x and x transpose y, I basically get a bunch of different ellipsoids, and each ellipsoid corresponds to a model. Right? So this is what happens if you do this method called analyze gauge. As I said, we don't really run away from the privacy utility trade-off, because what happened is, yes, we managed to to release the quantities in a private manner, but the utility might be terrible if there's a relatively degenerated direction. How bad can it be? Well, notice that if I had a direction that was truly degenerated, once I added noise, not truly meaning zero, but very small, once I added noise, it might become zero. So even a positive definite matrix, even if the matrix was full rank, and in all directions I had some signal, once I added noise, it might have canceled that signal. And now a matrix that before was invertible is no longer invertible. And that
What's the probability of a matrix going to degenerate from noise?
Well, this is exactly the plot. This is what is the probability of becoming invertible and non-invertible as a function of what is the minimal eigenvalue. Right? So the smaller the minimal eigenvalue, the less noise you need in order to make it cross the threshold to be 0.
Don't you need to hit exactly hitting exactly 0? It's
No, you don't. You need to become you become negative. Let's think.
a degenerate matrix doesn't. If you have an eigenvalue that's not 0, or if none of your eigenvalues are 0, then you're not degenerate.
Yeah,
Doesn't
it's a good
matter,
point. I need
positive or
to
negative.
think. No, you can become negative. No, yeah. You become negative, right? So what happens is you might have on your diagonal negative numbers.
Okay, yeah.
That way. No, negative numbers is no longer you. No. Then if you invert it, things go crazy.
Okay. Yeah.
Okay. So basically, what happens is you get negative numbers. That's like the first thing we need is to have the symmetry. You basically effectively broke the symmetry in a way, right? Because a positive semi-definite symmetric matrix, a diagonal must be non-negative. You took a matrix and multiplied it by itself, and now it breaks. So it can become negative, and any negative breaks it. You don't need the.
Yeah. That's not degenerate though. Degenerate.
Right, it's not degenerate, but it's like, yeah, but for the purposes of linear regression, it broke.
Useless.
Yeah. So, yeah, it's a good point. I need to use a more careful language. So analyze Gauss as is, not going to work. But now, what do you mean not going to work? There's a utility danger. So here comes a trick. Remember, I mentioned very early that there's another algorithm called ridge regression. What does ridge regression do? It's like linear regression, but I added this matrix. Now, with the hindsight of the language that we developed, we better understand what ridge regression does. Since X transpose X is the covariance matrix, and if I look at it in the coordinate system of this covariance matrix, its eigenvalues, this is basically a diagonal matrix with eigenvalues corresponding to the variability in different directions. This is exactly the spectrum that we saw before, right? This basically tells me that in this data set, there's one coordinate in which the variability is 1,000, and then there's a bunch where like about 10 and 1, and then there are a few that is practically 0. This is exactly what it tells us. So if I add some lambda times I matrix, I basically increased by an additive amount all of the eigenvalues by this lambda quantity. And since the probability that the added noise will cause the sign to be flipped it depends on the minimal eigenvalue. Well, if I increased it enough, I'm good. So this is the ADA SSP method. And ADA SSP is basically the same idea of analyze Gauss from the privacy perspective. You add a noise to X transpose X and to X transpose Y, but instead of computing the OLS, I compute the ridge regression, and by adding some value lambda that corresponds to the amount of noise I added, I can ensure that at least with high probability everything will be invertible. And in fact, more generally, I can say that for any epsilon and delta, I can choose the required amount of noise. For that amount of noise, I know how much I need to add lambda. And then for that lambda that I added, we know that is a classical result of what is the gap between the solution of the ridge regression to the solution of the linear regression. So I can put it all together and say for any epsilon, what is the utility loss that I get? And what is the result? It turns out to be, again, depending on the minimal eigenvalue. This is not the final expression. I will write the full one, but basically, this is what happens. What does it look like? So it looks like this. At first glance, it might not look very different from analyzed Gauss, but when you look at it, it has like, it's a bit longer, it's a bit further, pushed away further, in order to make it, to decrease the chance that something becomes degenerate in this direction. Okay. So this is ADA-SSP, and this is sort of the state of the art. I mean, what's considered state of the art now? The next technique that I will show, in some cases, is a little bit better. And anyway, this is state of the art only under the condition of bounded norm and range, etc. But in that sense, this is what we do. So here's the interesting thing. Remember last week, or even the week before, we started doing some complex things where we estimated the moments, and then we truncated, and then we estimate again, etc. But then we realized that from privacy perspective, we're using a single mechanism, Gaussian mechanism. Or later we had two mechanisms, exponential mechanism and the Gaussian mechanism. That's it. Here it's the same. We're still using only the Gaussian mechanism. What changed? What changed is that we are thinking much more carefully about what happens in the statistical process, and then we say, okay, what is the exact point in the process where I add the noise? And if I added that noise, what exactly is the effect on the statistics that we're trying to estimate, and therefore how can we mitigate it? And a large portion of what is done these days, the frontier research in private statistics and private machine learning, etc., corresponds to this. Oh, I have this particular algorithm for k-means. I have this for clustering, not necessarily k-means. I have this particular algorithm for subspace estimation, etc. Well, I can always do something like very general, like let's say subsample and aggregate. Yes, that's like a black box. But what can I get more out of thinking very carefully about the process and plugging in the noise in the right place? And the even more advanced things have to do in a way with what we did in the previous lectures. Like, wait, but if I have a assumption about the way the noise behaves, the way the distribution behaves, I assume it's close to low dimension, I assume all sorts of things. What can I do then? And privacy would never be able to use it, but we might be able to do something where the privacy is always guaranteed and the utility degrades only if the assumption is incorrect. I would just mention one more private technique just so we have another perspective. This one is called Gaussian sketching. So Gaussian sketching is the following thing. If I have a matrix, X, I can always multiply it either from the right or from the left by a matrix where all of the coordinates were IID sampled from a Gaussian. What will it do? So that for a moment, let's imagine that each row in this matrix has a constant sum. For simplicity, let's even assume it's 1. And for even more simplicity, let's assume all of its values are positive. I know this is not true, but this is like a useful, intuitive, intermediate thing. So if all rows or all columns, depending from which side I multiply, were non-positive and non-negative and sum up to 1, so basically each row corresponds to some mixture of the rows or the columns of the original matrix. Right? Because this is a Gaussian, there are like a few effects. There is the mixture, but there's also flipping the sign maybe, and there's also changing the scale. But still, in a way, it's projecting to some other dimension, sort of mixing the data. Mixing in what way? Well, depends where you multiply from. You multiply from the right, you're projecting to a lower dimension. Multiplying from the left, you're projecting to sort of a data set consisting of less points, in a way. Right? I had n, I multiplied by some matrix. I have now a new matrix of, let's say, k by d. Make a fictitious data set that sort of hopefully captures the essence. Why do that? For various reasons. When we multiply from the right, this is dimension reduction. This is a Johnson-Lindenstrauss transform. It's done for various purposes in the context of metric embedding. Doing it from the left, it's sort of a compression method. If you choose a dimension that's strictly larger than the, if you choose to project to a number of fictitious points that's strictly larger than the original dimension, you sort of have a smaller data set that stores all the relevant information to a relatively high degree of accuracy, and then for communication efficiency you can send it in a more efficient manner. As it turns out, what I just described also guarantees privacy. How? In a completely different way. So remember, what did we decide to do in the sufficient statistics method? We said we want to release X transpose X and X transpose Y. X transpose Y was just a linear query. So obviously adding noise is the most natural thing. X transpose X was a matrix, not a vector. So yes, that matrix had L2 norm bounded by 1, so we could add noise to all of it, but it had a weird effect. Here's another option we can do. X transpose X is a covariance. Let's imagine that is the covariance of some Gaussian with mean 0. Now, if I have a Gaussian and I sample a whole bunch of points from that Gaussian, and I compute the empirical covariance of the points that I sampled, this is a good approximation of the original covariance, right? That's why empirical estimation works. Well, here's something I can do. I will sample a bunch of vectors from a Gaussian with 0 mean and covariance X transpose X. Look at these points, estimate their empirical covariance, and use that as an approximation for X transpose X. If I can argue that this is a private process, I'm good. But the question is, what is the sensitivity of this new query, which is not a linear query, but the query which is sample a vector from a Gaussian where the mean is 0, but the covariance is the empirical covariance. And it just so happens to be that it's a leverage. Because the privacy utility trade-off would always be there, and it would always correspond to the leverage. And we would always have a large leverage having a large effect. So if you perturb the input, that point will have a large effect. If you perturb X transpose X, so X transpose X would not, doesn't need a lot of noise, but the effect on the utility will be large. And if you want to sample from the covariance, then the leverage is what has the big effect. And then, again, we need to do this ridge thing, but now we're adding the ridge. We're not sampling from X transpose X, we're sampling from X transpose X plus lambda I. But other than that, we're in the same world. And what we get is a different type of family. And what I want to point out here is not like what's better or worse in this method, is that this one has the effect that it's a bit closer to a circle, right? Because in analyze Gauss, we sample from the original covariance. We add the extra ridge term later when we're trying to do the before we're doing the inverse. But from privacy perspective, we already sampled, and here we added the lambda before in order to ensure that we have a large enough minimal eigenvalue. So it became a bit more of a circular thing. Better or worse? That depends on the properties of the specific eigenvalues of this problem, etc. But what I think is important to take out of here is that there are inherent properties of the distribution of the problem that govern whether the privacy utility trade-off will be good or bad, or to what extent. And then we can get around it. We will pay that price. But we can interject the noise and the privacy analysis in different points and get slightly different trade-offs. So for example, Gaussian sketching, the more modern version of it, is in some settings better than ADA-SSP, numerically definitely better, symptotically to some extent, but these are all like sort of lower order terms and things like that, because the essential trade-off is the same. So here we just have an example. So now this is a train and test mean square error of the original data set that we were using. This is what happens when you do the perfect linear regression. So obviously in the train error there is very small error, right? We don't get zero error because you can't explain perfectly. The test error is very similar. It looks like a line because relative to the others it's like really thin. Because there's no variability, because there's like a specific train in specific test. I didn't resample. So you see the difference is very small because it generalizes very well. Input perturbation is really terrible. The noise can be extremely large. And ADA-SSP and sketching, it seems that ADA-SSP in this regime is like ever so slightly better. But again, it depends on the setting and also the epsilon. Like it shows epsilon 1, epsilon 2, the trade-off might be different. Okay. The take-home message, besides, well, this is what happens in linear regression and this is how I can do it in a private manner, is this is another example of two concepts that I try to keep visiting back in this course. One is that the challenge of learning in a private manner is very close in its flavor to the challenge of learning in a robust or in a generalizable way. It's the same thing. It's not having one element affect too much my mental model of the world. And the only difference is that in privacy is no single element for even the most extreme data set, where statistics usually think of typical elements, or in robust statistic is like most of the data is typical and a small portion is atypical, etc. These is the difference. And that understanding that effect of a single element determines the privacy utility trade-off. And then the only thing that is left is to ask, well, where in the process of the estimation I can intervene in the way that will lead the best trade-off possible, or what is sometimes significant is a trade-off that in a typical case will be really good, and then in a crazy case will be bad, so that I don't pay for that possible crazy data set in the typical data set. Same way we had with the smooth sensitivity and proposed test release. Effectively, we're having here this kind of thing. For example, in the sketching, this is exactly proposed test release. How much do we increase the minimal eigenvalue? Well, we estimate the minimal eigenvalue and then add extra lambda proportional to that. And the same goes in ADA-SSP. You privately estimate it. So it's not proposed test release, it's proposed test calibrate or something like that, which is not just estimate something, if it's good enough, continue, if not, stop, but it's estimate something, and according to how good it is, add something or do something that improves it enough. But the same flavor will keep popping up in more and more algorithms. Questions? Okay. Thank you.